Welcome to the video lecture of compiler design. This video discusses the topic intermediate code generation of module 5. Let us have a look into the course outcome of this course, compiler design. The compiler design course has 5 course outcomes. This video presentation focuses on the third course outcome, translate high-level language into intermediate code statements. So that means at the end of this video presentation, the students will be able to translate given high-level language statement to intermediate code statements. This is the slide which is showing the syllabus of module 5. This video presentation focuses on the following topics: intermediate languages, graphical representation, three-address code, quadruples and triples under the intermediate code generation. First topic is intermediate code generation. As we know, intermediate codes, they are machine independent code. Even though they are machine independent, they are close to machine instruction, because from that intermediate code we are translating it into machine code. In the case of intermediate code generator, the input will be syntax tree, that is the annotated syntax tree from the semantic analyzer, and its output will be intermediate code. And from the phases of lexical analysis, syntax analysis, then semantic analysis and intermediate code, we can say that these all phases forms the front end of a compiler. Front end of a compiler means machine independent part. Intermediate code is actually a machine independent form. It does not depend upon the architectures of a particular machine. So we can say that intermediate code is a machine independent code. And what are the benefits of using this machine independent intermediate form? First one is retargeting is facilitated. Retargeting means different compilers can be created for different machines with different backend from an already existing front end. That means if you are given a backend, single backend, we can create different compilers for different machine architectures. Only the backend needs to be varied. So with a single front end, we can generate different compilers. That is the one benefit. Another benefit is that a machine independent code optimizer can be applied to intermediate representation. Since intermediate representation is a machine independent form, we have to optimize the code before generating the code machine instruction by the code generator. That is to make the execution faster. So we can apply the code optimizer to the machine independent phase, that is the intermediate representation. There is another benefit. So code optimization can be done also as a machine independent process. Next slide is intermediate languages. This intermediate representation can have different representation. First one is syntax tree, second is directed acyclic graph, third is postfix notation, and fourth is three-address code. So first is syntax tree, or another name is abstract syntax tree. It is the graphical intermediate representation. So syntax tree, it deposits the hierarchical structure of a source program. So syntax tree or abstract syntax tree is the graphical representation of the intermediate language. So we are covering the topic graphical representation under intermediate code generation here. And we know that a parse tree, it gives so many information. It can have attributes, its values for the attribute, like that. But in the case of abstract syntax tree, the parse tree will be compressed, or the condensed form of parse tree will be used in syntax tree. In the case of syntax tree, the leaf node will be numbers or identifiers, but the key intermediate nodes will be operators or keywords. Also, when we convert the parse tree into syntax tree, the single chain production will be collapsed. That is shown as an example here. The right hand side, the 3 star 5 plus 4n, that is given its parse tree along with its attribute values. And here we have converted that into the equivalent syntax tree 3 star 5 plus 4. It is shown in the left hand side. This is a compressed representation or condensed form of a parse tree is syntax tree is clear from this example. Next slide shows how we can construct programmatically a syntax tree. For constructing the syntax tree, function calls like creating operator node, creating leaf nodes are important. Operator node have two pointers also, left and right pointers, which can point to the child. Then leaf node has its it can hold the value of the identifier also the value of a number. Then it's pointed to symbol table entry also. So mk node of op comma left comma right, that is the function called for creating the operator node. Mk leaf of id comma entry is the function for creating leaf with a id identifier, and for leaf with value numerical value, we have to use the function called mk leaf of num comma val. Even though this function codes are existing, for building a particular syntax tree, we have to follow it sequentially. So that is shown as an example for the expression a minus 4 plus c. So if you are executing sequentially the a minus 4 plus c, we know that a minus 4 plus c leaf node will be a, 4 and c. And initially we have to compute a minus 4. So we have to create a first, then 4, then minus, that is the operator node. Then we have to perform the operation a minus 4 plus c. So that means c has to be constructed next. So c will be constructed as the leaf node. Then again you have to perform the operator node plus. That plus should have two left and right pointers. Left should point to the child node, which can compute the value of a minus 4. Then right pointer should be pointing to the c. So that is why p1 it is sequentially shown as p1 is equal to leaf mk leaf a, then p2 is equal to mk leaf 4, then p3 is equal to mk node minus, then fourth step p4 is equal to mk leaf c, and p5 mk leaf plus, and the pointers p3 and p4 they are pointing towards the result of a minus 4 and c respectively. So the result is shown in the left hand side. So next slide shows the another expression a is equal to b star minus c plus b star minus c. The syntax tree for the same is drawn, and two representation. Syntax tree it is a same syntax tree can be represented in two ways. One is in the tree form and another one is array of records. So the left hand side shows the tree structure, which has got the nodes with the pointers. Operator has two pointers, and leaf node has as leaf value and the pointer to symbol table entry. Then in the case of array of records, we know that id is the value of the identifier, then that token id, then the value is b, and there can be different fields, because maximum three different fields are possible, because in the operator node it can have the operator, then left and right pointers. Here the pointers are indicated by the location of the arrays, index of the arrays. Here consider the array record 3 at the index 3, star is the operator node, and the left and right pointers are 0 and 2. 0 holds the value of the first position, that is here id and b. So b star minus c we have to compute. So 0 stands for b, and 2 it is holding the value of minus c, unary minus c. So similarly all the other records has been arranged to represent the b star minus c plus b star minus c. Then another thing is that if you are given a syntax error definition, we can produce syntax tree for assignment statement. The example of the same, that means the semantic rules for the corresponding context-free grammar is shown, and this we can discuss in the next topic's presentation. The topic is assignment statement. It is coming in the next presentation of module 5. So that is all about syntax tree. Second representation is directed acyclic graph. The DAGs are also graphical representation. So this also covers the graphical representation topic coming under intermediate code generation. DAG means it is actually an easier method compared to syntax tree. It's equivalent to the syntax tree representation, but it will avoid so many branches, duplications. So here again we are considering the same example expression, that is a equal to b star minus c plus b star minus c. We can see that b star minus c is a common sub expression. It is computed 2 times. And the syntax tree is shown as different subtrees, b star u minus c. It is shown 2 times, but in the case of DAG it is shown only once. That is the main difference between the syntax tree and directed acyclic graph. It saves space also. So this is shown b star minus c, and so that is the example of directed acyclic graph. So coming into the description of DAG for expression, a DAG, directed acyclic graph on expression, identifies the common sub-expression in the expression. The interior node of the DAG represents the operator and its children represent its operands. Here another example is shown, a plus a star b minus c plus b minus c star d. So b minus c will be computed first. Here the common sub-expression is b minus c. So it will be occurring only once. Also here the 2 times a is appearing. That also in the DAG it is appeared only once. That is the difference between DAG and syntax tree. So this DAG, in a node in a DAG representing a common sub-expression has more than one parent, whereas in a syntax tree the common sub-expression will be represented as a duplicated subtree. Here we know that this a, b and c has minus, and this actually it is parent for plus and this star and this that is b minus c star d, a star b minus c, that is also evaluated. So here it is shown that that node has the leaf for a has 2 parents because a appears twice in the expression. More interestingly, the 2 occurrences of the common sub-expression b minus c are represented by one node. Then the node labeled minus, the node has 2 parents representing its 2 users in the sub-expression a star b minus c and b minus c star d. So minus b, it has got 2 parents, this star for computing b minus c star d and for a star b minus c. That is all about DAG. Third representation is postfix notation. Postfix notation is actually linearized representation. If we consider the same expression a equal to b star minus c plus b star minus c, we can generate a postfix string corresponding to that. The given string is in infix form. You can convert into postfix, or you can draw a syntax tree. Then you perform a postfix order of traversal. That is left, right, then root. That means if you have come to the left portion, that is a, and then traverse the syntax tree towards the right. When we have the right, it has got so many child. So you move to the leftmost child, that is b. Then you move to the right, that is c. Then you move to the u minus. Then you move to the root. So that subtree is completed, and so that left part is over. Again the plus has right child. So again you traverse the recursively perform the post order traversal, left, right, root. Left is b, then right is c, then u minus, then star. So we have completed the left, right, then come to the root, that is plus. Then here also we have completed the left, and this is the right, and this is the assign. So that is the example of a postfix notation. That is another form of intermediate representation. So next is the fourth form of intermediate representation, that is 3 address code. 3 address code is the important intermediate representation that we are following in this textbook. So it is a commonly asked question, which are the different intermediate form representation, and the 3 address code is the most important among them. 3 address code is a sequence of statements of the general form x equal to y op z, where x, y, z are names, constants or compiler generated temporaries, op is any operator. Listen to that. We use the term 3 address code because each statement usually contains 3 addresses, 2 for operand and 1 for the result. That means this is the result x, and we know that the operator is op and its operands are y and z. Maximum 2 operands, and 3 addresses, that is x can be stored in one address, y another address, z 3 address. So 3 address maximum possible. It's one operator. Then along with that operator we can also use assignment operator. That is why the name 3 address code. So all the statements will be of the form x equal to y opposite, maximum of 3 operands. So we can see an example of a 3 address code representation of the syntax tree or DAG. When we examine the syntax tree, the previously constructed A is equal to B star minus C plus B star minus C. This is the syntax tree representation, and we know that its corresponding 3 address code is, initially we have to in the case of expression A star, A is equal to B star minus C plus B star minus C, unary minus C is to be computed first. That is why T1 is equal to minus C. Then T2 is equal to B star T1. T1 is holding minus C. That is C. This is C unary minus is computed. Then B is computed. Then star. So that's value. This node's value is stored in T2. Then again coming to this part, T3 is equal to minus C, T4 is equal to B star T3, T3 is holding minus C, then T5 is equal to T2 plus T4. This is at T4 and this is at T2. So its result will be collected in T5, temporary variable T5, then A is assigned that value of T5. So this T are called temporaries, compiler generated temporaries. That is used in 3 address code. Similarly, for the DAG we can create the 3 address code. Here also initially we have to create T1 equal to minus C, then T2 is equal to B star T1, then T5 is equal to T2 plus T3. That means T2, the result is here. So what is the next thing you have to perform? A plus operation. The same B star minus C has to be summed up, T2 plus T2. It can be stored in another temporary. It can be sequentially numbered as T3. It's not a problem. A is equal to then T3. So that is the code for DAG. 3 address code corresponding for DAG. There are different types of 3 address statement. This is also very important. Types of 3 address statement. First one is assignment statement of the form. How we can represent using 3 address code the assignment statements. So x is equal to y opposite. It is an assignment statement. Is equal to is here. We are assigning the value of an expression y opposite to x. Op is a binary arithmetic or logical operation that statements can be converted into 3 address code. Then assignment instruction of the form x equal to op y. It is unary operation. Op is a unary operation. This type also can be constructed as 3 address code. Then third is copy statements. Copy statements means copy statements of the form x equal to y. X equal to y, where value of y is assigned to x. Then next one is unconditional jump of form go to L, which goes to a 3 address statement which is labeled with a L. Then conditional jump. If x relop y go to L, that means if this condition x is related to y, we have to implement the statement labeled with the L. Otherwise we have to execute the statement next to the given statement if x relop y go to L. So these are the different types of 3 address maze statement. Another one is parameter operations of the form. For a function call, we know that if the function is having 3 arguments, we have to call the function p. The function name is p, and that is shown with 3 arguments, and 3 arguments is a, param B, param c. Param a means a parameter of function. call p comma n, that means call function p with the n parameters. Return value y from function, optional. Here the p is a function with the 3 arguments a, b and c, that is shown as param a, param b, param c, and here no return value is mentioned. Another type of three-order statement is in-text assignments, that is in the case of arrays. X is equal to y of I, that means the yth arrays, array name is y, its ith location, the contents of the ith location will be assigned to x. The second statement, that is x of I is equal to y, indicates that what is the content of y that will be copied to the ith location of the array named x. Then now the limit of address is x, y and I. You cannot copy use the copy statements like x of I equal to y of j. Here 4 address x, y, I and j. That is not possible. Address and pointer assignments. X equal to ampersand y, that is x is set to the address of y. X is equal to star y, x set to the contents pointed to by y. Star x equal to y means contents of x set to value of y. So 8 different types of three-order statements are possible. Then how this can be implemented? Three-order statements are implemented as records with field for operators and operands. That is, we can use, there are 3 different representation: quadruple, triples and indirect triples. These are also very important topics. Again, we are considering the same example. The right hand side, it is given as a is equal to b star minus c plus b star minus c. It's 3 address code statements. T1 equal to minus c, T2 equal to b star T1, T3 equal to minus c, T4 equal to b star T3, T5 equal to T2 plus T4 equal to T5. These are the 3 address code statement we have constructed from the expression a equal to b star minus c plus b star minus c. How we can arrange this as quadruple, triple and indirect triple is the next slides. On the next slides we are discussing. Initially it is quadruple. Quadruple means 4. Quadra means 4. So we have the 4 fields: op, arg1, arg2 and result. In the quadruple representation, there are 4 fields for each instruction: op, arg1, arg2, result. So T1 equal to minus c, that was the initial statement. So the operator is u minus, unary minus, arg1 is c, arg2 we can give it as a blank. Then result will be stored in a temporary variable T1. Again, T2 is equal to b star T1. So that is b star, that is by the previous slide, b star T1. That is the second statement. And so this op will be star, then b, then T1. Result will be stored in T2. Again, the next statement u minus c, then T3, then star b, T3, T4. So b star minus c is computed 2 times. Then now it is assigning its computed values. That is, before that it will be summing up, that is T2 and T4. Then its result will be stored in T5. Then that will be finally assigned to A. Here the features of quadruple is that unary ops don't use arg2. You can see that u minus will not use arg2. Param don't use either arg2 or result. Param A is only there. Jump put the target label into result. Jump go to label L. That means it will put in the result field the jumps. The contents of field arg1, arg2 and result are normally pointers to the symbol table entry. So these are all the quadruples are having the values, and these values arg1, arg2 and result can be identifiers or number values. It can be or temporary values. It will be always the pointer to symbol table location. Here the one thing you had noticed that the temporary names must be entered in the symbol table as they are created. That is very important point. Temporary names are also entered into the symbol table. Triple means, as the name implies, there will be 3 fields: op, arg1 and arg2. We have avoided that result field. That is how we have done, is that we have instead of that result field we have used the statement number itself. Result of an operation x of y is referred to by its position. That is, here we know that the minus c, the result will be stored in 0. So B 0, that will be shown in parenthesized values within bracket. So that temporary variables has been eliminated and the positions has been shown. To avoid entering temporary names into the symbol table, here there is no temporary, so that will be not be entered into the symbol table. Then since 3 fields are used, it is also called as triples, sometimes called as 2 address code, because only 2 address are possible, one is operator. Parenthesized numbers represent pointers into triple structure, while symbol table pointers are represented by name themselves. Here the C will be a pointer to the symbol table, but in the case of parenthesized numbers 0, this 2 and 3, they will be simply pointers into the triple structure. C itself is a pointer to this triples. Then 2 is a pointer to this triple structure. That is about triple. And more triple representation, that is x of I equal to y. How we will compute? Initially we have to compute the array location, starting location, then the I location, then that will be assigned to this operator, and then we have to copy the content of y to whatever we have computed in this 0th position. Similarly, x equal to yi, ith location, then y the name of the array, then that y of I is computed here in the 0th position of this triple, then x and 0, that will be assigned, that is x will be assigned the value of the result at the position 0. Next is indirect triple. Indirect triple, it is holding another table of pointers that will show the pointer to the triples. Here already there will be a triple table, and into that triple table we will be holding another array which holds the pointers to this triple. So these triples are numbered like 14, 15, 16 sequentially. Then the 0 will be pointing towards the 14, 1 will be pointing towards 15. Interaction, 2 will be indirectly pointing to 16, 3 will be 17, 4 will be 18, 5 will be 19. So indirect triples use listing pointers to triples. Then we have 3 representation for the 3 address code implementation: quadruple, triple and indirect triple. We can compare all the 3. First one, it's saying that quadruple is good. That means if when we produce a target code, that is a machine code, all the temporary names as well as the programmer defined names will be assigned some memory location, runtime memory location, and this will be entered in the simple table entry of that data. But if you're using quadruple notation, it will be easy for that temporary to find out the location. But this is not possible with the triples, because triples don't have location for temporary variables associated with the symbol table. Also, another thing is that in the case of quadruples, if the statements can be moved, we can make the optimization easier, because the next phase of intermediate code is optimization. While we do optimization, the statements might be needed to be changed. The order might be needed to be changed. So in that particular situation, if you are using a quadruple, it will not cause any problem. It will not cause any change to the table structure of the quadruple, because the result will be stored in temporary variables that will not be changed. So this is achieved because using quadruple notation, the symbol table interposes higher degree of interaction between computation of a value and its use. Also in the case of that means the value is computed and stored in a temporary variable. It is highly interacted. Then with quadruple notation, if you move a statement compared to x, the statement using x requires no change. That means the order of statement, that is in the case of quadruple, this 0, if it has changed that order, here it comes, this u1 minus c, it comes to the 6th position. If you are adding to the 5th, this is shifted to 5th. That means it has it is not an issue, because that statement numbers are nowhere associated. So rearranging the statements in a quadruple will not cause any problems. That is what it is said. But in the case of triples, it is affected. In the case of indirect triple also, it will not be affected because 0 is indirectly pointing to 14. So if you arrange 0 in the position of 3, that can also point to 14. So there will not be any problem because this triple stable will not get any change when we reorder the statement here. That is one comparison or observation when we compare the representation. Then comparing the space utilization, quadruple and indirect triple somewhat require same amount of space. But if same temporary value is used more than 1 in indirect triple, it can save some space, because you know that in the case of b star minus c, in the indirect triple, that is u minus c, so 14 and 16 can be clubbed. This 14 and 16, same op or r1 r2 fields, so 14 and 16 can be clubbed. Similarly 15 and 17 also can be clubbed, so we can save somewhat more space compared to quadruple in the case of indirect triple. Triple requires less space for storage compared to the above two. You know that since there is no point additional tables or something else, so triples will be consuming very less space compared to quadruples or indirect triples. So as a summary of comparison, quadruples can provide direct access of the location for temporaries because the temporaries have symbol table entries, and it is easier for optimization. While we reorder the statement, there will be not create an issue. Triple, space efficiency, only benefit is that it has got space efficiency. Indirect triple, it is easier for optimization because the reordering, it will not cause an issue or create an issue. And second point is that space efficiency of the indirect triple. So that is all about intermediate representation. Thank you.